Here we go. I apologize. I am in the airport right now waiting for a plane that has been delayed back from Costa Rica. All right, cool. Before we get started, here we go. Introduction to statistics.
I'll kick you in the face.
So we use statistics a lot in this class. Scientists typically collect data on a sample of the population. We use that to infer what's happening in the general population. So, for example, we can't go around and measure every tree in the world. We pick a sample of that, and we're able to kind of infer what's going on in that population. Pause here to take notes. Awesome. So, the first step in an analysis is to graph the data and examine the distribution. So, typically we'll see a normal distribution here. You can see, here we go. So, normal distribution has that peak in the middle, and it goes down on each side. So, that's what we call normal distribution. We call it a bell curve. It's a bell curve, shaped like a bell. Let's talk a bit about, pause here to take notes. Cool. All right, central tendencies. So we measure central tendencies. It's a descriptive statistical analysis that allows for researchers to describe and quantify data between different data sets. The center of distribution can be described. We talk about this in mean, median, and mode. So we'll be doing a lot of mean, median, and mode throughout this class. These are called the central tendencies. So mean, median, and mode. Mean being the average, median is the middle number, and mode is the number that is seen the most. So let's talk about mean. Mean is the average of the data set. This looks like a crazy equation here, but all it really is the average is each point in the data set, x1, x2, x3, all the way over to the end of it, divided by the total number of data sets. It's an average. You guys know how to do this. Add them all up, divide them by the number that's there. So sum all the data points of the data set, then divide it by this number by the total points of the data. And that's how you get your mean. So here's the formula for you. These formulas are given to you on the AP exam. You don't have to remember them. So pause here to take notes. Great. Let's practice. A student biology class planted 5 tomato seeds in separate containers. They exposed the seeds to an artificial light source for 20 days. At the end of the 20 days, the students measured the height of the tomato plant that grew from those seeds. The data is below. There's our data. Get it? Got it? Good. So, what is the mean of the data? How are you going to do this? They have
that doesn't fit your personality.
Okay, so we're looking for the mean, which is one of our central tendencies. So how we're going to do this, step 1, we're going to add up all the data points. 65, 52, 71, 56, and 61, that equals 305. Then we're going to divide it by the sum of the number of data points. So we got 5 here. 1, 2, 3, 4, 5. We measured 5 different things. So we're going to take our 305, divide it by 5, and our average is 61. So the mean for the sample of these 5 plants is 61. How does this apply to the general population? So if the students went out and collected hundreds of samples of tomato plants growing under these same conditions and graphed the data, they should find the center of distribution to be about 61 millimeters. So that is our central tendency. The center of the distribution is going to be about 61 millimeters. Or 61 millimeters, yeah. So when we look at our bell curve, 61 should be like right up there. Do that pen style. There we go. So if we look at our graph here and we plot out all of our data, right there in the middle would be 61. Get it? Got it? Good. Pause here to take notes. Let's look at our median. So our median is the middle number in a range of data points. The trick to this is you have to arrange the data points in numerical order first. The median's the middle number. If there's an even number of data points, you average the 2 in the middle, right? So if you're looking at 10 data points, you can have 5 on one side, 5 on the other, and nothing in the middle. What you would do is you would do 4 and 4, and then average the 2 numbers in the middle.
They got what? They got fruit. Fruit?
So the median is useful in data sets that have measurements with extreme values or abnormal distribution, which we will see, especially in some of our hands-on practical labs, is the data is the data. So sometimes we'll have extreme or abnormal distribution of data. It is what it is. So why do we do this? The median is not distorted by extreme or large or small values, right? So even if we have these extreme data points on either side, if we could figure out the median, it's not going to be affected by those extreme values. So that's one of the reasons why we use this as one of our central tendencies. Pause here to take notes. All right, let's practice. A group of Labrador retrievers. Oops, let me get my highlighter. Cool. A group of Labrador retrievers is training for the police academy. One test is the sniff test, where police dogs time how long it takes for dogs to find a scent. They collected the data on a group of 9 dogs. The data is in the table below. So here we go. You can see the 9 dogs. You can see the time in seconds. And you can also see we have some outliers here. So there's 21 versus 180, right? So that's a huge range. So what would the median be? Taking a look at our data set, first thing we're going to do is arrange the numbers in numerical order, lowest to highest. So lowest here is 21, highest is 180. All right, then we need to find the middle value. So what I like to do is just go ahead and cross off 1, 2, 2, 3,
You know that's true.
3, 4,
Teachers are
4.
notorious for that.
So there you go, that's 48. Sorry, Mr. Ortez just showed me a mean. But 48 is the middle value. I find it easiest to cross them out, 1 and 1. If you're left with 2 in the middle, you would average them. So the median's 48. This would mean that 69.9, which is much higher value than the median, because of the extreme low and high values of the data set. Therefore, the median is a better measure of our central tendencies. It gives us a better idea of what's going on inside the data. Pause here and take minutes. All right, mode. The mode is the value that appears the most in the data set. It's only useful when describing distribution of data where the mean and median would not be appropriate. So this is like our last resort central tendency. Not usually used to measure the central tendency, but here we are. Bimodal distribution. So this is what we're looking at as a bimodal distribution. Is that there's distribution here and there's distribution here, and then it sort of drops off in the middle. All right, let's do a quick review. What are the 3 measures of central tendency? You guys know this. It's the mean, median, and mode. Which measure of central tendency is best for data sets that have abnormal values, extreme high and low outliers, and why is this the best measure of central tendency? Again, we're going to be using this a lot, the median, by when we're analyzing our data sets that we gather from our hands-on labs, right? Median is the best because it's not distorted by those large or small measurements. Great, pause here to take notes. So this practice problem you're going to do on your own. Let's read it together. Researchers are interested in how long students spend on the TikTok app per day. They take a random sample of 10 high school students who use an iPhone. They examine the amount of time each student spends on TikTok by looking at their screen time for one whole day. The data is below. So we have 10 students right here, and here's our times. You can see, again, we have some outliers, 201 minutes a day versus 10 minutes a day. For this data set, determine the mean, median, and mode, then identify which measure of central tendency would be most accurate for this data set. Please answer this question on your own. I'm going to be looking for it in your packets.
You had to be there.
I know. There you go. Great.
You had to be there.
All right, let's talk about variability in our data. We're going to see a lot of variability in our data. It's just how science works. We're going to get these outliers. It's not a big deal. So variability is the measure of how far a data set diverges from the central tendency. So you have the mean, median, and mode, and the variability is how much it diverges from that. It's how spread out the data points are. It's measured by a range called the standard deviation. And you guys might see this in some of your statistics classes or some of your other classes. Pause here to take notes. So one of the measures of variability is the range. It's the difference between the largest and smallest values. The easiest way to do this is to subtract the largest from the smallest value. The larger a range indicates a greater spread of data. Larger range means a greater variability. Smaller range means less variability. That means that the data is less different from each other, right? Often used in conjunction with standard deviation. So we're going to talk about standard deviation in just 1 second. Pause here to take notes. So let's look back at the data for the tomato plants. What's the range? So here's our tomato plants again. We measured 5 plants. We have the data down over here. Easiest way to do this is subtract the smallest number from the largest number, so you find the difference. 71 is the largest number, 52 is the smallest. So you can see that there's a range of 19 millimeters. Great. So, standard deviation is something that we've mentioned a few times already. Let's talk about it. So a standard deviation is a measure of how spread out the data is from the mean. So the low standard deviation means the data is closer to the mean, and the independent variables causing the changes. High standard deviation means the data points are more spread out. So how this looks is you'll have a data set here, okay? Remember our normal distribution bell curve right there, with this being our mean. If you have a low standard deviation, it's going to look more like this, right? Low standard deviation. Most of the values are close to the mean. If you have a high standard deviation, it's going to look more like this, with a lot of the values further away from the mean. So if it's more spread out, it's high standard deviation. If it's closer together, it's low standard deviation. High standard deviation just means that factors other than the independent variable are likely causing the changes. Remember, the independent variable is the variable that you guys are going to be changing. So we want the independent variable to be causing the changes. Low standard deviation is what we're going for here. So you can see here, low standard deviation is tall and thin. High standard deviation is low and fat. We're looking for low standard deviation. So, 1 standard deviation from the mean in either direction on the horizontal axis represents 68% of the data, right? So if you are saying that there's a data point that is within 1 standard deviation from the mean, then that is really great. That means 68% of the data hangs out in there. 2 standard deviations from the mean will include 95% of your data. This is one of the reasons why scientists say 95% of the time, or 0.95 is a p-value. Because we want 95% of our data to be just 2 standard deviations away from the mean. 3 standard deviations from the mean will include 99% of your data, right? So even some of those outliers get included in there. We're really looking for all of our data to be within 2 standard deviations. If it's within 1, that's great, but generally that doesn't happen. Right, so here we are. Here's the mean. This is 1 standard deviation out from the mean. You can see 31.4, 31.4, so that would be 68. Right, so that's 1 standard deviation out, and this includes 68% of the data. If you go 2 standard deviations out on either side, that includes all of this data, right? Everything in between here. So the only thing that's left is this out here. Right, those are your outliers. So 2 standard deviations should represent 95% of your data, and then 3 standard deviations, which includes this whole thing, will include 99% of your data. So that's all that standard deviations mean. 1 standard deviation of the mean on either side. 2 standard deviations is 2 out on either side. 3 standard deviations is 3 out on either side. Get it? Got it? Good. Boom, this is what I just did. 68% of the data falls between plus or minus 1 standard deviation of the mean. 95% of the data falls between plus or minus 2 standard deviations of the mean. And 99% of the data falls within 3 standard deviations of the mean. So this is like your normal bell curve. This is really what we're going for here. here's how you get your standard deviation. Again, this is not an equation that you need to remember. This equation will be given to you. So, standard deviation is represented by S. Sum of is this value here. You guys know that that means sum of. These are your measured values. So the sum of all of your measured values here and the mean of those values squared. All right, so remember PEMDAS, right? Parentheses, exponents, multiplication, division. Down here is your degrees of freedom. We call it degrees of freedom. All that is the number of data points that you have minus 1. So if we're going back to the tomato plants, there was 5 tomato plants. We're going to minus 1 from that. Our degrees of freedom is 4. Okay? Pretty simple. All right, there are 4 steps to solve for standard deviation. Step 1, find the mean. So find the average of all the data. Step 2, determine the deviation from the mean for each data point and square it. That's this thing right here. Right? The measured value of the data point and the mean. And you're going to do this for each data point as well. So determine the deviation from the mean for each data point and square it, calculate the degrees of freedom, and put it all together. So that's the step 2 solving for standard deviation. Let's practice. Here we are back with our plants. We're going to use the data from the tomato plant experiment. So first step, we're going to find the mean of all these heights right here. Okay? Remember, it's 61. We did that in the earlier example. Step 2, determine the deviation from the mean for each data point and square it. So it's helpful to set up a table like this. 65, which is the value here, minus 61, which is your mean, equals 4. 4 squared is 16. And you're going to do this all the way down the line. Now, if your data point is less than the mean, that's okay. Just make sure you do negative. When you square a negative number, it becomes positive. So you're going to do this all the way down the line. Boom. Done. Did you see how we did that? The data point itself, which is represented by x, and the mean, which is represented by x with a little line on top of it. Once you get those values, then you just square them. All right, so we're doing this step by step. Step 3, determine the degrees of freedom. Easy. It's the number of data points minus 1. Then you put it all together. So you will add all of these up. 16, 81, 100, 25, and 0. That would be this top value. And then you would divide it by 4. So total here is 222. You're going to divide it by 4, do a square root. So your standard deviation, is 7.45. So what does that mean? We got a standard deviation value. What does that really mean? 1s of 61 would be plus or minus 7.45. Okay, so you would do 61 plus 7.45. And then minus 7.45. So anywhere between 53.55 and 68.45, and that is one standard deviation. So that should include 68% of your data. 68% of your data should fall between these two numbers. 2 standard deviations would be plus or minus 61, so your mean, plus or minus this times 2, right? Because we're in 2s. All right? So that means 95% of all of your data should fall between 46 and 75.9. And 3 standard deviations, same thing. You're just going to take the s, you're going to do 3s times with 2235. So that means that 99% of all your data should fall between these two values. If you want to, here are some links for standard deviation. I'll post this on Classrooms. You'll be able to go in and watch it yourself. All right, let's look at standard error. So, standard error of the mean is used to determine the precision and confidence of the mean value. How well does the mean of the sample represent the true mean of the population? So this is sort of a way for us to figure out whether these outliers are too far outliers or close enough to the mean that we can kind of loop them in. So it's based on variability, the number of data points. Okay, so these two things are what the standard error is based on. Low standard error means increasing confidence. So that means that I have low errors, commonly given as plus or minus 2 SE, right? Standard errors, that means it's 95% confidence. This is, again, when scientists say, I am 95% sure, and that means they're 100. If a scientist ever tells you they're 95% sure, it means they're 100% sure. Okay? Here's the equation. Again, you're not going to have to remember this. This will be given to you. So you have standard error of the mean here, standard deviation, square root of the sample size. So you're going to have to find all three. Pause here to take notes. All right, let's practice. So let's use the data we calculated for the tomato plant. We have our standard deviation, we have our sample size. So all we're going to do is plug and play. 7.45 divided by the square root of 5. There you go. Standard error of the mean, 3.3. Yes, I know it says 6. Standard error of the mean. This means that each measurement varies, plus or minus, but 3.3 from the mean itself. So if we have our mean, remember, as 61, you could do plus or minus 3.3 from the mean. That would be your standard error. All right, this is how we, there we go. So this is how we do it. Standard error is plus or minus, right? 3.33 is pretty low. It's a low standard error, so that's good. That's high confidence. Low error is high confidence. Okay, so you have here, this is your 61 right here. And all you do is take your standard error, and it says plus or minus. That means you add and you subtract. So you're going to add 3.33 to 61. That's the 64.3. Let me erase my stuff. Right, 6433 right up top. And then you would, that's your adding. Then you would subtract. 61 minus 3.33. You put a line down below, and then you connect them. That's it. That's all you do. This means plus or minus, right? So you're going to take this value, add it to it, and also subtract it from it. Make sense? Get it? Got it? Good. Here you go. Here's a video. I'll post this on Classrooms as well. You can watch this in your own time. All right. So now we got all of our data. We have our error bars. So taking a look over here, we have 4 trials. We're measuring height in millimeters, right? You have 1, 2, and then you have your standard errors. If error bars overlap, the difference is not significant. We talk a lot about significant and non-significant differences, right? Not significant just means if they do not overlap, the difference may be significant, right? All that means is that we are trying to determine whether the changes that we see are a result of our independent variable or some other outside force that we do not have control over, right? Notice that for each trial, the error bars overlap. This tells us that the difference seen is not significant. See how they overlap 1 and 2? So they overlap right here. These ones don't overlap. Okay. Oops, sorry, I keep going. These definitely overlap. These ones overlap as well. Right, so this difference is seen is not significant, meaning the difference that we see in this data is due to our independent variable and not some outside force. Great. Cool. Pause here to take notes. And that's it. I will see you guys in class. Thank you so much.